Welcome everybody to the distinguished colloquium jointly hosted by TILOS and HDSI. So today we're thrilled to have Professor Becca Willett from U Chicago. Most of us know Becca here, but let me still do the introduction to allow people who join late to hear the full version of the talk. So Rebecca Willett is a professor of statistics and computer science and the director of AI in the Data Science Institute at U Chicago. She also has a courtesy appointment in TTIC, the Toyota Technical Institute at Chicago. Her research focuses on machine learning foundations, scientific machine learning, and signal processing. Becca received various awards, including inaugural data science career prize from SIAM Society, was named a fellow of the Society of Industrial and Applied Mathematics, and named a fellow of IEEE. She is also deputy director for research at NSF Simons Foundation, National Institute for Theory of Mathematics, Theory and Mathematics in Biology, deputy director for research at the NSF Simons Institute for AI in the Sky, a member of NSF Institute for Foundation of Data Science Executive Committee.
You don't have to be
right. Okay. Yeah, I guess people have joined. So many more awards to read, but maybe you get the idea. Without further ado, let's welcome Becca.
Thank you.
Thank you very much. Actually, I just want to, can I hide this? Is this, oh, this one, right? Oh, perfect. Good. Oh, thank you so much for inviting me. It's a real pleasure to be here. Really enjoying the San Diego weather. And I'm excited to tell you about some very recent work that I've been doing with my joint postdoc with Rena Barber, Jake Soloff. And we've been studying algorithmic stability. So to start, I want to show you a video that I watched on YouTube a number of years ago, showing a BBC documentary, nature documentary, showing an ice bear or a polar bear walking around on some ice. And what they did is they fed each frame of this video into what at the time was a state-of-the-art image recognition system, trying to see what label it produced for each frame in the video. So what you're going to see is at the top, the frame of the video. And then on the bottom, it's showing you what this image recognition system is outputting. So in this particular frame, for instance, it's saying that it's got a, I don't know, maybe 65% likelihood that it's an ice bear, maybe 15% likelihood it's a white wolf, and 15% likelihood that it's a black bear, or something along those lines. So as we proceed, for many frames, it's correctly recognizing the ice bear, as we would hope. But then with very small changes in the bear's appearance, all of a sudden, it gives completely wrong predictions, and ice bear isn't even in the top 3. So with just these are not adversarial examples, nobody's adding noise or anything, but you can see that with very subtle changes in the frame, you get totally different predictions of what the content of the image is. And so this is a deep concern, I think, because as we start thinking about using these kinds of tools in various high stakes contexts related to healthcare, national security, science, and engineering, we don't want to have very small perturbations to cause huge changes. And so what we saw in this video is that small changes in the test features can lead to large changes in the predicted class. And a related question is, if we were to perturb our training data, would that give us completely different predictions? And it seems very plausible that that would be the case, right? If we see that what we've learned is so sensitive to small changes in the test features, then it certainly seems believable that just small changes to the training data could cause big changes in the predictor. And so this leads me to this notion of algorithmic stability. So let's imagine that we've got a training data set, XY pairs, and then we're given a new test point X. And we want to predict the corresponding label for that. So we're going to refer to a learning algorithm, script A, which operates on a training data set D. And what it gives us is some predictor that we would call F hat. So for instance, A would correspond to the process of training a neural network on our training data using weight decay and an atom optimizer. And then F hat would correspond to the fully trained neural network that we are then going to deploy. So when we talk about algorithmic stability, what we want is the following. If we were to take our training data and just remove one sample, then we would like the corresponding predictor trained using the exact same setup, right? So for instance, again, using a neural network with atom and weight decay, we'd like the resulting predictor to not be too different. So in this picture in the bottom, we've got two different learned decision boundaries, one using all the training samples and one using all but one of the training samples. And you can see that the training boundaries can be very different. So this would be an example of something that's not very stable. So algorithmic stability is important for a wide range of problems. And the reason for it is because, well, what algorithmic stability gives us is the following. If we were to look at leave one out errors, so if I were to leave out a training sample, train a predictor, and then see what it predicts on that training sample, we would hope those leave one out predictions would be representative of what we might see on some future test data, right? And so having algorithmic stability so that leave one out predictors are not too different every time we leave out a different sample is important for understanding test errors. So in particular, there have been works that have shown that having a stable algorithm is important to leading to generalization guarantees. So for a new test data point, say xn+1, we would like that the expected value of the predicted label is close to the true label. Or the expected value of the error between the two is small. In addition, people often use tools like cross-validation to choose various parameters of learning algorithms. And this only really works if we can get accurate estimates of the test error, and stability is an important component of that, as we discussed. It's also related to, algorithmic stability is also related to characterizing when the risk of an algorithm can be driven to zero. And it's also related to coming up with prediction intervals. So if we want our learning algorithm, not just to make a prediction, but to give us something like confidence bounds or prediction intervals, then in order for us to be able to compute prediction intervals, we need stable algorithms. So how can we ensure that algorithms are stable? First of all, you might be saying, well, aren't they already stable? Like, is this a real problem? But even something as run-of-the-mill as least squares can be unstable, right? So for instance, if D, the dimension of our feature space, is approximately equal to N, the number of training samples, then this can be very unstable. So over on the left, we have a setting where N is very big relative to D. So we've got an overdetermined system. And what we can see in this plot is that the predictions using all the data, all the training data, versus the predictions using all but one of the samples are very, very similar to one another. So that's behaving in a stable way. But on the right, where D is 100 and N is 105, so they're very close to one another, it's still overdetermined, but just barely. There we can see that for many different test points, the prediction of the method trained on all the samples versus all but one of the samples can give very different predictions. So even something as simple as least squares has regimes where it can be unstable. And then, of course, many of us are interested in far more complicated methods like neural networks, where there's all kinds of bells and whistles, right? We've got convolutional layers, we've got max pooling, we've got flattening. This picture doesn't show it, but we might have residual connections. And so trying to analyze and prove something about the stability of a very complicated system like this is, honestly, I think probably hopeless. And so what is what can we possibly do? One thing you might try to do or think of trying to do is to have some kind of certification strategy, right? Like you hand me a black box neural network, say, and I try to just test it out or probe it with some samples and tell you, yeah, it looks like it's stable. It turns out that there are impossibility results that tell us that we cannot do this. That just given a black box algorithm, unless we basically have an unrealistically large, holdout data set that we never use to train, and an enormous computational budget so that we can do like a brute force search. Unless those things are true, it's just going to be impossible to certify that an algorithm is stable. So then we could ask a follow-on question, which is, if you give me a black box algorithm, is there some way that I can put a wrapper around it or alter it in order to convert it into a stable algorithm without making it a bad algorithm, right? I could certainly put a wrapper around it, which says every time you give me an output, I'm just going to map that output to 0. That's pretty stable, but it's not very useful. So we want something that's going to do some post-processing on an algorithm to ensure that the outputs are stable, and yet is still going to maintain the good performance that we associated with the predictors, the base predictors. Okay, so people have been thinking about stability for many years. Back in 1996, in the book Heuristics of Instability and Stabilization in Model Selection, Riemann said, given that instability has undesirable consequences, what can be done? And he notes unstable procedures can be stabilized. And this brings us to bagging. So bagging is a concept that I think many of us have seen in maybe even an intro-level machine learning class. So at the top here, I've got a number of different colored circles that would correspond to training samples. And what I'm going to do is I'm going to take random subsets of those training samples, and each of those I'm going to call a bag. And I'm going to train a predictor on each one of, oops, excuse me. Sorry, got a little crazy here. I'm going to train a predictor on each one of those different bags, on each one of those different subsets. And then what I'm going to do is I'm going to average all of those different learned models. So for a test point, little x, I would compute the prediction for f hat 1, f hat 2, f hat 3, and I would average those together, and that would be my final prediction. And so I'm going to denote this as a tilde b. So the tilde tells us that we're doing some bagging, and b would be the number of different bags, and in my graphic, that's 3. And so this is the basic concept of bagging, and people have used it over the years in the context of stability in a number of different ways. So first, just a little bit of nomenclature or some technical details. So classical bagging or bootstrapping based methods would choose these bags, each to have, say, m different training samples in them. And the P would be the probability of any individual sample being in one of the bags. So they're going to sample with replacement. And so this probability P would be 1 minus 1 over n to the n. And alternatively, we could consider something like sub-bagging, where we're going to sample uniformly without replacement. And there, the probability P of a sample being in a bag is just m over n. And we're going to consider both of these different variants today. So first of all, empirically, we can see that bagging promotes stability. So Jake did tests in the context of logistic regression, neural networks, regression trees. And in each of these cases, what we're looking at is a histogram of leave one out perturbations. So he's looking to see how different the prediction is when we train on all the training data versus the prediction when we train on all but one of the training samples. So a stable method is going to have those leave one out perturbations be very small most of the time. And what we can see in red is that if we take the base algorithm, say logistic regression at the top, and we look at these leave one out perturbations, then this has a very large support. There's a large number of times where that leave one out perturbation is quite sizable. But in contrast, if we were to take logistic regression and then apply bagging, then what we see is that those leave one out perturbations are much smaller. This histogram is much more concentrated, close to 0. So this is true for all the different methods that we tried. And there's a rich existing literature looking at the performance of bagging in various specific contexts, both in the context of trying to develop some theory and in the context of looking at empirical performance. So random forest, variable selection and regression, classification when we've got class imbalances, robust Bayesian inference, all of these have looked at bagging in different forms.
So the leave one out plus bagging, you were basically taking one sample out, then doing bagging on the rest of the samples.
Yes, that's right. Exactly right. So when I have this f hat minus I, that ith training sample is now not appearing in any of the bags. Yeah. So there have been a number of different explanations posited for why bagging does give us this increased stability when we look at things empirically. So there have been arguments that it reduces the variance associated with estimators. The theoretical work in this space are asymptotic analyses, and they assume that the algorithm, the learning algorithm, has some strong regularity properties. People have also thought about it as a smoothing operation. And this is effective and leads to some nice bounds when we place strong assumptions on the distribution of the training data. People have looked at it from the perspective of equalizing influence. So high leverage observations or outliers are going to be de-emphasized by bagging. And then explicitly, people have looked at bagging in the context of algorithmic stability as we are here today. But past theory has really focused on regimes where the size of each bag, the number of samples in each bag is small relative to the size of the total data set, or they assume that the original base algorithm A is stable. So we would like to understand when bagging gives us stability, but make minimal assumptions, right? In the world of modern machine learning and neural networks, I don't want to have to assume that my algorithm is already a little bit stable in order to get more stability. I don't want to have to assume that I know that the distribution of my training data adheres to some properties that would be hard to verify, or is, say, Gaussian, which our training data typically is not. And so I want to avoid as many assumptions as possible about my base algorithm and about my training data. So we're going to consider, I want to give a precise definition of algorithmic stability now, because I was a little bit hand wavy before. So we say that a learning algorithm A is epsilon delta stable if for any training data set D and any test point X, I can do the following. So I'm going to look at the predictor that I learn with all of my training samples and what it outputs for X. And then I'm going to look at the predictor if I leave one training sample out. And I want to count how many different times the difference, the perturbation of those predictions is greater than epsilon. And basically, I'm going to look at the frequency of those perturbations exceeding epsilon by looking at all the different leave one out predictors. And so I say that my method is stable if that fraction of times my leave one out perturbation exceeds epsilon is less than delta. And there's a, oh, yes. No.
So here is square on the right side of this summation is what does this stand for? This stand for the frequency or the ratio?
So first of all, I'm just talking about tail stability right now. So I think you're maybe looking at the next one.
No.
Oh, what's square? Oh, sorry. This is like the indicator function.
Oh.
Yes, sorry. That's supposed to be a like Blackboard bold I. Sorry. Yeah, thank you for asking. Right. So it really is like a bold I for an indicator function. Yeah.
This is not the old bagging, only over the randomized algorithms. You fix the training data set,
So the training data set is fixed. We do allow, I tried to keep the notation light. We do allow that the algorithm is randomized. So for instance, for each different predictor, I might have, I've got a different, say draw of my initial parameters for my neural network training or something. So we do allow for some randomization there. So the probability would be with respect to that. And also we're choosing these bags at random. Yeah. But yes, the training data set is fixed and is holds for any test point. So it can be adversarially chosen, for instance. So this is just a definition. I haven't proven anything yet. We also have a notion of mean square stability, which will come up in a little bit. But we say that an algorithm is beta squared stable if for any training data set D and any test point X, if we look at the squared leave one out perturbation and average that over all the different samples we might leave out, that average is less than some level beta squared. Okay, so here's the main result. So as I said before, we can talk about either bagging or sub-bagging, depending on whether we're sampling or drawing samples for these bags with or without replacement. But in both cases, we're going to let P denote the likelihood of any individual sample showing up in a particular bag. And so P, which depends on both how many training samples I have and the size of each bag, is going to be the core kind of quantity that shows up in our theorem. So the theorem says the following. Let's let A be any kind of base learning algorithm that returns predictions that are bounded between 0 and 1. Then for any number of training samples N, any bag size M, and then we have that bagging with, in this case, an infinite number of bags, is going to satisfy this mean square stability with level beta squared, as long as beta squared is greater than 1 over 4n minus 1 times p over 1 minus p. And from here, we can show that this also means that we will achieve this epsilon delta squared or delta tail stability as long as epsilon squared delta is greater than beta squared. Okay, so there's a lot to unpack here, and I just want to kind of highlight some of the features and aspects of this theorem. So first, so here I am just kind of stating this on the top again. So let's just consider an example. Let's imagine that we had a training data set with 10,000 training samples, and each bag has got half of the training samples. And epsilon, the size of the perturbation, leave one out perturbation that we're worried about, is 0.01. Then what this says is that we should be able to achieve epsilon delta stability for any delta less than or greater than 2.5%. Now, critically, this theorem applies to any base algorithm that's giving me outputs between 0 and 1. So the base algorithm could be highly unstable. So unlike past results that assumed that the base algorithm was at least moderately stable, we don't have to make any assumptions about that base algorithm except that it's giving us bounded outputs. It holds deterministically, holds for any training data set and any test point. So I don't have to assume that my training data is Gaussian, for instance, or well-behaved in some sense. I'm showing all of these theorems is in the limit as the number of bags go to infinity, but we also have extensions to finite numbers of bags, randomized algorithms, as we talked about earlier, and unbounded outputs. Okay. In addition, we can gain some insights into the role of epsilon and delta here. So I mentioned that in the past, some analyses of bagging assumed that the number of samples in each bag was very small relative to the total number of training samples. this might not be desirable. For instance, if I'm training a neural network, maybe I need lots of samples to get good performance. And so constraining myself to have really small bags might give me something that's stable, but which has really bad predictions. So here we have a lot of flexibility in how we choose the size of each bag. So for instance, we can work in a proportional subsampling regime where M is on the order of N. So for instance, M could just be half of N for if you wished. So if that were the sampling regime that you wanted to be in, if that's how big you wanted your bags to be, then in order to have this bagged method be stable, you would need delta epsilon squared to be greater than 1 over N. Or if you wanted to, let's go straight to the bottom, be in a minimal subsampling regime where you want to keep your bags as big as possible because maybe your method is really data hungry, like a neural network. So if M was going to be equal to N minus, say, for instance, square root of N, then we're going to have a stable method after bagging as long as epsilon squared delta is greater than 1 over the square root of N. So this is giving us concrete insights into how the size of the bag relates to algorithmic stability. So let me give you a little bit of intuition for why we're able to achieve stability in this broad range of settings that's frankly quite a bit broader than some of the past work that's studied bagging. So we start with N data points, as I said before. And then let's say we consider, so each one of these is a different sample. And then we're going to form all of these different bags on the bottom, which has a different subset of M different samples. So each one of them is going to be used to train a predictor, and our final model is going to be the average of all those predictions. So if we were to consider a particular training point, xi, yi, and we look at all the different bags that contain that training point, none of those bags are going to appear when we do our leave one out prediction, right? When we do leave one out, when we train with everything except the ith sample, all of these bags are unavailable to us because they contain the ith sample. And so now we are just left with the other predictors. And our leave one out prediction is the average of all the bags that do not contain that ith sample. Okay. So to understand why bagging gives us stability, imagine that we've got some number K of bad training samples. And they're bad in the sense that I have written at the bottom here, where if I leave out that sample, then I get a really big perturbation in the predictions that I'm going to output. Okay, so let's imagine that we've got K of those. Then what can we say about the stability? So in particular, what we can do, what we're interested in when we study algorithmic stability is the sum over I of all of these leave one out perturbations. Now, if I only have K bad points, then this quantity, which I'm just going to call L1 for brevity, that quantity is lower bounded by K times epsilon, the size of the perturbation. Pretty straightforward there. In addition, a typical bag is going to have, on average, K times P bad points, but there's some fluctuations, right? Some bags are going to have more than that, some are going to have fewer than that. So overall, they're going to have pk plus or minus the square root of kp 1 minus p, bad points. So now what I'm going to do is I'm going to try to upper bound this L1 quantity, the sum of all the leave one out perturbations. And what I can show is that that L1 error has a bound that looks like this. And this is kind of complicated looking. But basically what I'm doing is I'm summing over all the possible samples that I might leave out. I'm looking at the sign of the leave one out error times an indicator of whether that sample I is one of the bad ones or not, and whether it's in bag B. And I'm looking at the variance across all the different bags B. And so what we can do is we can bound this as follows. So the 1 over 1 minus p is just coming from below, and the numerator here is reflecting the fluctuation in how many different bad points are in any individual bag. So now I've got upper and lower bounds on this quantity L1, right? Right from the beginning, I had this lower bound K epsilon, and now I've got this upper bound up here. So if I put the upper and lower bounds together, I get this inequality here. So what's happening is that as I increase the number of bad points that I have to worry about, the lower bound is increasing linearly with K. The upper bound is also increasing, but not as quickly. Because as I increase K, the number of bad points, then each bag is going to have more and more bad points. And so the variation across bags containing a particular bad point isn't going to be too big because all of the algorithm outputs are bounded. So this variance in here is not going to grow too quickly with K. And so because the lower bound is growing more quickly with K than the upper bound, what we can do is we can show that the number of bad points can't be too big. And in fact, it has to be bounded by n times this level delta, where epsilon times, epsilon squared times delta adheres to this bound showing up in our theory. So essentially what we're saying is that bagging is giving us this stability because the way that we prove this is that we show that the number of bad points that give us bad leave one out perturbations cannot be too large. Okay, so let me show you some empirical examples. So if we look at the upper left to start, here we've trained a neural network on a regression task. And in red, what we're showing is the value of delta versus the value of square root of n times epsilon. So we're giving a sense of how unstable this method is, because if I had a target, say, error tolerance level epsilon, then this is giving me a sense of how frequently I'm going to have the fraction of leave one out predictions exceed that error tolerance epsilon, and in this case, it can be quite large. Our stability guarantee corresponds to this dashed line. And so what we're saying is that after bagging, that we are going to be able to get stability that's somehow to the below and to the left of this dashed line. And empirically, we see this blue line is indeed below and to the left of that dashed line. So for any target error tolerance epsilon, let's say let's say square root n times epsilon is 1, then the likelihood of us, or the fraction of times with which we're going to exceed that is very small, in this case, like 0.05. Here's another example with a regression tree. So the regression tree is not stable in the sense that this curve, this epsilon delta curve, is kind of up and to the right. And yet, after applying bagging, as people have examined previously with regression trees, we see that our method has become far more stable and adheres to the theoretical guarantee. And then finally, in the bottom, we've got an example with logistic regression. Now, logistic regression is an interesting example because when in blue, the number of samples is, with logistic regression, we have both stable and unstable regimes. And so in blue, what we see is that when the method is already stable, then after we apply, or I'm sorry, I guess I've got in the solid lines, once I apply sub-bagging, I am not hurting my stability at all. But with the dashed lines where I'm in an unstable regime, then I can see that applying bagging increases my stability. So we said from the beginning that our goal was that when we have a method that's unstable, we're going to drag it into a stable regime and hopefully not make our performance worse. And that's in fact what we are seeing. Yes.
You put it that it still works for when you have finite number of bags. Do you know how the error would depend on the number of bags?
We get an additive term. We're just using a Hufting-Azuma inequality. And so we get a term that depends on what 1 over B.
Because I was imagining the worst case scenario where the base algorithm just randomly picks a point from the bag and output it. Then essentially what bagging does, I guess, is that you would have more of those points aggregated, right?
Yeah. Right. So certainly having a very small number of bags adversely affects the bounds as one would expect. So in particular, right, in this theorem, right, this delta epsilon squared, the lower bound on it would have an additional term. So plus like 1 over B. So if B gets very, very small, then all of a sudden these curves look much, much worse. But of course, nobody's really bagging with 1 bag either. But yes, our bounds do generalize to finite bags. I'm just not presenting them here.
So in these plots, the stable versus unstable, that's the factor of overdetermination, right? So this can.
Right. So just like we saw with least squares, if n was approximately d, it was unstable. It's a little bit different with logistic regression. Here, the unstable regime is when n is equal to 2d. So that's when we're very unstable. As soon as we get up to n is equal to 4d, then we're already stable. And so bagging doesn't provide additional stability, but it also is not hurting our stability in any way. But in the unstable regime, it's bringing us, bagging provides additional stability. And so what we're seeing is that without bagging, there can be a big difference in the level of stability of logistic regression, depending on how oversampled we are. But post-bagging, the level of stability is very similar. Okay, so everything we focused on so far has been just on regression, where we're trying to make a scalar output or a scalar prediction. Of course, most problems that we're working on in machine learning are not in that regime. So many algorithms return outputs that are much more complex, like we're trying to estimate a discrete distribution or a probability density, or trying to perform parametric regression. And so the examples or the stability results that I've described so far extend into settings where the output of our learning algorithm is something that's is a point in a Hilbert space. So in particular, analogous to how we assumed that our base algorithm before gave us bounded outputs, here we're assuming that our base algorithm gives us outputs within a bounded subset of the Hilbert space that we're calling W, and rad of W is corresponding to the radius of that space. And so we can talk about stability in that Hilbert space. We can define mean squared stability in a way that's analogous to the way we described mean square stability before, using the expected value of the mean square or of the mean perturbation, leave one out perturbation. But now we're just measuring that perturbation within the Hilbert space using the Hilbert space norm. And so what we can show again is that bagging of these algorithms that make outputs that are within a Hilbert space is guaranteed to yield mean squared stability as long as this stability level beta squared is sufficiently big in a way that depends on the radius of this output space, the number of training samples, and this likelihood P of any individual sample showing up in any individual bag. Okay, so this feels maybe a little bit esoteric, but there are, well, first of all, there are concrete examples that I just highlighted where it's extremely important. But what I want to do is show one particular application of this idea in a setting that's maybe relevant to many of us, which is classification. So now our goal is to make a prediction of a class label. And we're going to assume that there are L possible class labels. Again, we've got training data and a test point X. And we're going to say that our learning algorithm, now C, for a classifier, is going to output a mapping from a test point to a set of labels. And so informally, this classifier is going to be stable if we leave out one of the training samples, the class predictions are not hugely different. So what past work has done has really focused on the stability of the predicted class posterior probabilities, but does not address the stability of the predicted label. So if we go back to, well, first let me just define these quantities. So we can think about a classification algorithm as having two components. First, this algorithm A is going to output weights on each of the different classes. So sort of like the likelihood of the class being class 1 or class 2, given my input vector X. And then second, we've got a selection method that's going to actually choose which labels to output. So for instance, we could train a neural network that assigns weights to each class label for an input X. And then second, we could have a selection method, which for instance could be the argmax. It's just going to choose whichever class has the highest posterior probability. So if we go back to our ice bear example from before, on this particular frame, we had at the bottom here that the method thought it was a baboon with 22% probability, an ice bear with 0.21 probability, and gorilla with weight 0.13. And so now if we wanted to translate this vector of weights to a predicted label, we might say, well, I'll just predict whatever label has the biggest weight. And in that case, in this case, it would be the baboon. So what I'm trying to say is that even when these weights are very stable, so even if I leave out a training sample and the weights don't change very much, that can still lead to a very big difference in which class is ultimately selected, right? The weights don't have to change very much for me to predict ice bear versus baboon by just choosing whichever class has the biggest weight. So all of the stuff I've said about stability and regression, or stability of these weight vectors, is not guaranteeing any kind of stability for my classifier. This has been a widely studied issue. And as a result, when you look, for instance, at, say, the computer vision literature, typically people report things like top K accuracy, say top 5 accuracy or top 10 accuracy. So what they do is this selection component of the algorithm, where it's selecting what labels to return to the user, it's going to return K different labels. Instead of just returning one label, it's going to return K. And we say that it's going to get an accuracy score of 1 for that test sample if the true label is among any of the K that were returned. So in this ice bear example, for instance, the top 1 accuracy is 0 because the highest weighted label is baboon, but the top 2 accuracy is 1 because the second highest one is correct, it's the ice bear. So this is a reasonable, maybe empirical thing to do, but it does have drawbacks, because if we look at another frame here, right, there's a huge posterior likelihood that it's an ice bear, and yet a top 2 selection rule is going to return both ice bear and white wolf, even though we've got a huge amount of confidence in it being an ice bear. And so it's naturally sort of inefficient. It's not adapting to the uncertainty associated with our predictor. So this is suboptimal in that sense. So here's what we're going to do. We've got our training set. Here I'm going to think about like the fashion MNIST data. So I've got a bunch of different pictures of clothes and labels. I'm going to train some learning algorithm, and then I've got a test point. Now I'm going to look at these predicted probabilities. And for instance, I could just choose the argmax, which in this case is dress. And then if I were to get, if I were to leave out one of the training samples and train my learning algorithm again, and then choose the argmax, I might choose bag. And if I were to leave out a different training sample, train a different classifier and look at the weights and choose the argmax, I might choose coat. Okay, so this is highly unstable. So again, we're going to use the concept of bagging as a starting point. Same idea as before, only now the output of the bagging are these weight vectors, telling me sort of the likelihood of each of the different classes given an input X. Now I could revisit this example where I'm doing bagging here as my first step for learning an algorithm for outputting the weights. And then again, I'm going to have my selection correspond to choosing whichever class has the biggest weight. So in this example, I've got Y hat as a bag. And now if I were to remove one of my training samples, then Y hat is a coat. And if I remove a different training sample, Y hat is a shirt. So this is highlighting that we've applied bagging in this first stage for outputting the weights. The weights are now guaranteed to be stable, but that's not yielding stability in the final output label. So to address this challenge, we're going to do a little bit more than bagging. So in our first stage, we're going to apply bagging to get stable weight vectors, these W hats. And then in the second stage, we're going to alter the selection rule. We're going to use something called the inflated argmax. So instead of just choosing the single class that has the highest weight, what we're going to do is we're going to choose a selection or a collection of different labels that are almost maximizers of these weights. And this is going to be robust to small perturbations in the weights. And what we're going to do is we're going to see that by doing this, we're going to get a collection of selected labels that's consistent in the sense that if I were to leave out a training sample, then there's some overlap between the output collection of labels that I get with the full data set, with the full training set versus with the leave one out training set. So to illustrate this, on the left, I've got an illustration. Sorry, I have something messed up here. I've got an illustration of the inflated argmax in the setting where there are 3 possible labels: dress, coat, and shirt. So if I get a weight vector W, it's going to be somewhere on this simplex. And what the argmax is doing is it's saying which corner of the simplex am I closest to. So if that weight vector is anywhere in this blue polygon, then the selected label is going to be dress. What the inflated argmax is doing is it's saying there are going to be these boundary regions where I cannot reliably decide among or stably choose among the different class labels. And so if I am sufficiently close to one of these vertices, then I'm going to select that label. And if I am not, then I might return a collection of labels reflecting that uncertainty. So what the inflated argmax is doing is if a label is in this inflated argmax, what it means is that class L would have had the largest weight in this weight vector W by some margin if the weights were slightly perturbed. And in this case, the size of the margin and the weight perturbations both scale with epsilon. I've got a formal definition here, but I think what I want to do is highlight this in action. So in this case, for instance, if I'm combining bagging with this inflated argmax selection rule, then in this case, the vector of weights has got 2 weights that are high above the rest. And what the inflated argmax would do is return both bag and coat for this sample. And if I were to leave out one of the training samples and then look at this test point, again, I've got a different set of weights, but they're not too different because I have the stability guarantee of bagging. And when I apply the inflated argmax, again, it tells me it could be a bag, it could be a coat, it's ambiguous. And if I get a new test sample, then I get a new set of weights, and the inflated argmax reflects the ambiguity or the similarity of the top weights. And so it's giving me shirt or coat or dress. So unlike these top K rules that in no way reflect that for some samples, I've got a lot of certainty, and for other samples, I have a lot of ambiguity. Here, we're adapting to the inherent uncertainty reflected in these weight vectors. And what we have is a stability guarantee associated with this combined method, where we're combining both bagging and this inflated argmax. So in particular, we say that we have selection stability if the selected classes associated with all the training samples and the selected labels associated with all but one of the training samples, if those have some overlap, if they're somehow consistent with one another. And we can prove that selection stability is achieved for appropriate levels of epsilon and delta, just as we saw before when we were looking at some of the initial bagging results. And so if we look at a fashion MNIST experiment here, where we've got 60,000 training samples in 10 different classes of garments, and if we just train a simple convolutional neural network on this data, and then apply bagging and use the inflated argmax. What I'm going to do is I'm going to measure the instability of this approach or of any, a couple of comparison approaches by looking at this measure of inconsistency that I was just talking about in the theory. And so what we're seeing here are lines for 4 different approaches. The red dashed line is where we started, where we've got a basic base algorithm, say the CNN, plus choosing the argmax. And what we're seeing is that for any kind of target instability level delta, the frequency with which we are somehow exceeding that, that level is quite high. And so then we can say, well, what if we just used the standard argmax, but we applied bagging on the weights? So that's the solid red line. And we can see that that improves our stability by a wide margin, but it alone is not sufficient to get us as much stability as we might hope for. In the dashed blue line, we see what happens if we use just the plain old CNN without bagging, but we use this inflated argmax selection rule. And there we see that alone is not enough to really give us a stable learning method. But the combination of the two, the combination of bagging with this inflated argmax, you can barely even see the line because it's so far in the bottom left-hand corner, is giving us a huge amount of stability in the classification output. Okay, so I know there's just a couple of minutes left, but I just want to show you one final, hopefully quick example related to model selection. Okay, so here's one context in which people might use model selection. They might say, I've got a linear regression setting, and I'm going to try to estimate my coefficients, a sparse set of coefficients using the lasso. And what I'm interested in doing, oh, yes.
So this overlap criterion, can it be kind of trivially expected if you output a very big set?
Yeah, that's true. So, and I think I just glossed right over that. So, so we don't have guarantees on the size of the set that's output. That's something that does vary with algorithm and data set and other things. But what we see empirically in this fashion MNIST example, for instance, is that the average set size is 1.02. So what we're seeing empirically is that most of the time it is just outputting one class, but when there's ambiguity, it's outputting more than one class. But that's rare. And yet we're still achieving this high level of stability, right? Yeah, great question. I'm glad you mentioned that. Okay, so with model selection, I'm curious, I would like to know what covariates in X are most important for making a prediction of the label Y. So what I might do is I might try to estimate the covariates using something like the lasso, for instance, and get an estimate beta hat of the covariates. And then my model selection or my selection stage is just going to say, when are elements of beta greater than 0? Or the absolute values are greater than 0. So this is very commonly used. It also is super unstable when we have highly correlated covariates. So what I have in the lower right image here is a view of the covariance matrix for my training data. And so what we can see is that covariates 1 and 2 are highly correlated, and 3, 4, and 5 are highly correlated with one another. So if my true model were that the expected value of Y given X is just X1 plus X3, then hopefully my model selection method would tell me X1 and X3 are the important covariates. But you can see because of these high correlations that it's equally plausible that it would tell me X1 and X4 are important, or X2 and X5 are important. And so this can be extremely unstable as a result of the correlations. So this feels a little abstract, but there are regimes in, say, AI and science where this is extremely salient. For instance, what people will often do is they will make observations of a dynamical system. This is the Lorenz 63 system, and the governing equations are here on the right. But you could imagine a scenario where I don't actually know those equations. I only get to make observations of the data, and I want to estimate what those governing equations are. And so people have been exploring different tools for estimating those governing equations. And one particularly famous example is SIND, sparse identification of nonlinear dynamics. And so what they do is they say, I'm going to expand these equations in some basis or library of different terms. And all I need to do is estimate weights on those terms. And so they use the lasso. So everything we were talking about with sparse regression, they're using in this context to try to learn governing equations. So in this, and so what we'd like to do is we'd like to understand how to make this stable. We'd like to ensure that we get the same model, even if we were to leave out one of our training samples. And what we can do effectively is treat this as an example of the classification setting that we were just looking at. So before we had L different classes, here what we're saying is each candidate model just corresponds to one of our different class labels. And so we can look at using the same kind of ideas. I want to be careful about your time, but we're using the same kinds of ideas. And so when we apply the inflated argmax plus bagging to this model selection problem, again, we're achieving guaranteed levels of stability. And we can also see that it's working well in several different senses. So first of all, if we were to look at on the far left, the frequency with which we achieve a target level delta of stability, we see from this empirical CDF that we are sort of at the very top left of this plot, which is the most stable of all the methods that we looked at, including a top K selection rule that I talked about before. Now you might ask, well, are we achieving stability by just outputting stupid models that I say output 0 all the time? And the answer is no. So in the middle, what we're seeing is that the utility weighted accuracy of our method is also higher than it is for any other method across a wide range of instability levels. And then finally, to the earlier question, the number of selected models is not huge. So we are not achieving stability just by saying, well, I have no idea, it could be any model. That would be very stable, but also vacuous. And we see this not only in this sparse regression example that I led off with, but also in things like equation discovery, where we've got data reflecting, for instance, a Lotka-Volterra model of predator-prey relationships. And so again, we can use the same kinds of ideas for these kinds of data sets. And we can see again that the combination of bagging and the inflated argmax gives us stable predictions of the model that are highly accurate and that are not too huge, so huge as to be vacuous. There's a number of open questions that I've kind of barely touched on. One thing is computational complexity. There's a question earlier about how many bags we really need, and obviously that's extremely salient to the computational complexity challenge. And in addition, we've defined some new notions of stability in new context, and I think this could potentially present new opportunities for understanding generalization outside of regression context. So thank you very much. I've covered several different papers here with my co-authors. And as Jan mentioned at the beginning, this is joint work with a collection of variety of institutes at the University of Chicago. Thank you very much. Yes.
I had a question about your proof sketch.
Okay.
I think you said that when you're looking at the leave one out prediction, it's like throwing away all the bags that had a certain observation in them, right?
Mm-hmm.
So isn't that looking at like the form of stability after sampling? Is that the same as thinking about the stability of this process where you bag all the data points and then
I'm not sure what you mean about stability after sampling, but let's just take a quick look. So, right. So here I'm just for this illustration, showing an exhaustive collection of every possible bag, every possible distinct bag that has M distinct samples in it. So there's N, choose M of them. So my bagged result here is F hat. And my claim is that this particular F hat, after doing the bagging is stable. So now I have to look at a corresponding bagged estimator where I don't use the ith sample. And that's why what I'm doing is I'm saying, okay, if I take a particular sample yi, then I cannot use any bag that contained that sample xi, yi. So I'm only and because I started off with an exhaustive subset of every possible bag, once I delete the bags that contain xi, yi, then what I'm left with is an exhaustive set of all of the bags that don't contain that sample. Yeah. And that's what I want to compare with when I'm trying to prove that the bagging or the bagged algorithm is stable. Yeah. Sorry.
Quick question. So the classical paper of generalization and stability,
Mhm.
at least it's on both cases,
Right.
find the stability to be on the loss function, right? The difference is the loss function was to add up, remove every one of the data points and the uniform stability, the average stability, etc. And that stability notion directly imply generalization of different kinds, right? So is your definition for stability stronger or weaker, or is it compatible?
So our results extend to giving us guarantees or stability guarantees relative to a loss function.
With the loss exceptions.
Yeah, and we're still assuming that we've got bounded outputs, which ensures that in turn that the loss is going to be bounded. And so that's a simple extension. I do think though that in this Bousquet and LSF work, that the stability guarantees are relative to the same loss that you use during training. And that's not a requirement for our method. So we are not saying or for our guarantees. So you can just give me a loss function and I can tell you something about stability relative to that loss, whether or not that was the loss that you used for training. Yeah. Yes.
For previous stability, they can get some generalization guarantee. So for this new defined epsilon delta stability, can we get some generalization guarantee?
Right. So if you look at sort of what's required for the generalization guarantee that's outlined in this Bousquet and LSF paper, for instance, it's saying, assuming that you've got a certain level of stability for your algorithm, here is the generalization guarantee. So what we're saying is, okay, you can't make that assumption for, say, a neural network, right? But if you were to apply bagging to your neural network, then you are guaranteed to have stability, and therefore you do have a generalization guarantee for your bagged neural network. Assuming that you've chosen your bag size appropriately, you have to be a little bit careful here. But yes, so what we're saying is that by using bagging in this way, you're going to be able to directly get to generalization guarantees for the bagged method. Did I overstate some?
Just if we apply the bagging, we can get satisfy the stability guarantee, but it's not directly a generalization guarantee.
That's right. So what I'm trying to say is that generalization guarantees have been proven already in past literature for stable algorithms. And so what I'm presenting is a way to get an algorithm that's guaranteed to be stable. So once you have a stable algorithm, then you can use existing work that applies to stable algorithms to get generalization guarantees. So it's sort of like a precursor to getting generalization guarantees. Yeah.
Yeah, I think we'll just do the quick one.
Yeah. So how much information is lost? So say that it's trivial to output the constant, and that would have absolute stability. So you have your function, you're doing bagging, that seems to me loses some information.
Right. So this is where, or why we look at things like the accuracy of the bagged predictor. And this is something that we do not have any kind of guarantees on. And I think that's what you're getting at, right? Like, is my bagged predictor less accurate than my unbagged predictor? And certainly that can happen. And so because we are working in this assumption-free regime, it's very hard to get guarantees on accuracy. Nevertheless, as I was highlighting in the classification and model selection examples, what we are seeing is that empirically, we are getting high levels of accuracy, but there's no guarantee that if you were to use some different architecture or something else.
Because there's a hope for some guarantees under more assumption.
Oh, yeah, under more assumptions, sure, right? Like, we're not making any assumptions at all here about the base algorithm. So your base algorithm could be a random number generator, and we can stabilize that, but nobody cares. So yeah, you would need to be able to you would need more assumptions if you wanted to say anything about accuracy. But what we've seen empirically across a number of different algorithms and commonly used training sets is that these methods are still giving us high accuracy in reasonable settings.
Quick question. So the algorithm also has some parameters, right? And so when you are doing bagging, you are also increasing the number of parameters. So how do you know that the stability is not from the increase in the number of parameters?
So I've got two parameters that I can play with. One is M, the number of samples in each bag, and the other is B, the number of bags.
Yeah, but there's also parameters in the algorithm, like logistic regression. So
Oh, I see. Yeah.
Now you have like B number of those weight vectors.
B number of.
So one logistic regression will have some, let's say, n parameters. But now when you are bagging, you are doing n times B parameters, right?
I guess what you're saying is, how do I do cross-validation for like a bagged algorithm?
No, because each model trained on each bag has a different set of parameters or weight vectors.
Okay, so let's just think about logistic regression. I've got this penalty parameter lambda, say, right? So I think when people talk about a learning algorithm, they're talking about, it's something that's going to work with a particular, well, how do I want to say this? So if I go back to the way I kind of formulated this most generally. Sorry. Where was it? Here. Okay, so a learning algorithm accepts a data set D and returns a model F hat. So if I'm thinking about logistic regression, my algorithm is going to take in my data set and it's somehow going to say, for instance, use cross-validation to choose a good value of lambda and result in a predictor that corresponds to a single fixed lambda. So I can imagine A here as encapsulating any kind of hyperparameter tuning, for instance. I don't know that that's the most efficient way that you would want to run something like this in practice, but I'm not kind of returning outputs for a whole range of different hyperparameters. I'm assuming that my algorithm is giving me a single predictor that in your setting would correspond to a final choice of lambdas, for instance.
The bag method, now you have like three different predictors, right? And then each predictor will have parameters.
Right, so in bagging, right, we have this little picture. So we've got B different predictions, and our final prediction is the average of all the B different sub-predictions.
The predictor which was trained on unbagged data had actually less number of parameters.
So you expect the accuracy, not the stability.
But like, can there be a bigger parameter which is trained on the whole data set, which is as stable as the bag?
What parameter are you talking about?
For example, the neural network has weights, right?
Yeah.
So, but if I want to do bagging on that neural network, I have to train B number of those copies of that neural network.
Right.
So now I've actually increased the number of weights. Right?
Okay, yeah.
So I'm just saying that there could have been a bigger neural network,
Mm-hmm.
which was as stable as the bag.
As
I-
accurate, not as stable.
Yeah,
I'm talking about accuracy. Stability and accuracy are two different things.
But yeah, I'm not
Yeah.
sure because we are comparing a smaller model against a larger. model.
There's a computation trade-off.
yeah. So if you were to say, just use all of your training samples and have a network that's B times as big, right? Like I've, multiplied the number of layers times B, or I've multiplied the width times B, then yes, that maybe would be more accurate because you're more over parameterized or something, but there's no stability guarantee associated with that. And you're not going to, in most cases, be able to have any kind of generalization guarantee. So it might look nice on some holdout data set, but that's not the same as a generalization guarantee. So you can, you're right, make just a bigger model and train it with all of your training data sets, but that will not lead to stability guarantees. And in fact, maybe less stable.
Maybe let's take the rest.
All right. Thank you very much.